5, we're primarily looking at chapter 6. Okay, test 5 is primarily chapter 6. So section 6.1 through 6.3. We did a lot. We really, kind of overemphasized a lot of these questions between our lab, between that worksheet, your homework, your problem sets, your in-class examples. So these should be pretty familiar with you by now. I expect people to do really well on this test. The idea of conservation, conservation of momentum is similar to conservation of energy, except it's even easier. With conservation of energy, you had to think about, was there potential? Was it kinetic? Was it a spring? There's no types of momentum here. We're only looking at linear momentum. We're not looking at rotational. We don't have to worry about anything spinning. If something was spinning and moving, it'd have two types of momentum. We're only looking at one-dimensional linear momentum. So you have momentum before the collision equals the momentum after the collision. That's our general rule that we're going to look at. We're going to look at the idea that what the heck? Why are these lights 1 and 4? We're going to look at the conservation of momentum here between two independent objects, that may become stuck together after the collision or may start it together before the collision. So, in section 6.1, we talked about momentum, and momentum was defined as the product between an object's mass and its velocity. You're rarely going to be given a question. I'll tell you now, you won't be given a simple question like that in the test where it says find the momentum, because all you have to do is take mass times velocity. I might give you a multiple choice where it says which of the following objects has the most momentum. So maybe you have to calculate the momentum for 4 objects, compare them, see which one has the most momentum. If, say, an object had a velocity of -8 meters per second and a mass of 5, its momentum would be -40 meters per second. What does the negative indicate when you're looking at momentum? If I said the momentum is -40 kilograms meters per second, what does the negative indicate?
Maybe the velocity is going to the left.
Yeah, it's just moving left. So if 3 objects are there, one has a momentum of -40, one has a momentum of 20, another has a momentum of 10. -40 is the most of the 3, even though it's a negative number. So when you're looking at and you say which of the following has the most momentum, the negative sign doesn't really affect the quantity of momentum, it just affects the direction of motion of that object. After we looked at momentum, we looked at momentum impulse theory. And in momentum impulse theory, we said the following. Delta P equals force times time, where this quantity itself right here is called impulse. Force times time, that product is impulse. So when you're looking at these problems, the change in an object's momentum is always equal to its impulse. So if you could determine how much that object's momentum changed by looking at the change in velocity, you can find out, say, the unknown force if you know the time. Or find the time period of contact if you know the force that was applied. So an example of this, we'll do examples in a minute, but an example in words would be like, an object is traveling at 5 meters per second and its mass is 8 kilograms. If it collides with a railing and bounces off the railing with a velocity of -2 meters per second, and the time of contact where it hits the railing is 0.5 seconds, determine the force the railing pushes back with. Well, in that case, you're solving for F. You know the time of contact T. You can find the change in momentum, remembering that delta P really means momentum before minus momentum after. So remembering that this is really PF minus PI equals FT. Remembering that PF is really MVF minus MVI. So this, in the end, is the formula you're going to end up using. Okay, the boxed in one. The one that's given is above that, 2 lines up. Now, if I told you, though, that the change in an object's momentum is 20 kilogram meters per second, that's what delta P is. I'd be telling you that, versus being told the mass and velocity and having to calculate it. So you need to utilize the units in the problem. If the problem says something in kilogram meters per second, I'll write it on the board here. Okay, kilogram times meters per second. Those are the units. That is momentum. That's what delta P would be in this problem. If it says the object's momentum changes by 40 kilogram meters per second, that's what goes in for delta P up here. And then maybe you just have to divide by time, or just divide by force, depending on what you're solving for. Okay? Are we all focused in that back row? This review is for you to understand, not for you to do other work in this class. So if I find out that's what you're doing, I'm going to send you downstairs in a moment. Focus on what we're doing. If you're told about the change in momentum, that's what delta P actually is. If you're given a mass, an initial, and a final velocity, you need to calculate delta P using this formula down here. It depends on the scenario at hand. Yeah?
I was saying, your momentum, your units always going to be kilogram.
Always. Yep. This is always the units of momentum. If a problem says find the impulse, find the impulse. You can't find F by itself. You can't find T by itself. You're finding what Ft is. So if a problem said find the impulse, it really means just find out what this is right here. If you can figure out what the delta P is, well, delta P is the impulse. Change in momentum is equal to impulse. That's why we call this the momentum impulse theory. So if you ever want to find the impulse, but you know nothing about force or time, just find out what the change in momentum is. If you found out the change in momentum to be 40 kilogram meters per second, that is the impulse. Okay, again, impulse and momentum, or change in momentum, are really the same thing in essence. If you're trying to find force, then you would divide by t and get it. But if you're just finding the impulse, solve for or evaluate whatever's on this side of the equation, and that's what the impulse actually is.
So first, here you would give us the final momentum was about the initial momentum, if we're trying to find time force.
Sure, if you're trying to solve for one of these things, you need either these numbers or you need the mass and the velocities to find out what the force might be. Sure.
And then there is a question on the problem set about falling from a surface, a table or something. And obviously if your leg is relaxed, you won't deal with as much pain. Whereas
think about the egg example I gave you in class where you were tossing the egg. How would you catch it?
Well, yeah, you catch it. Yeah, I understand. Like, how would you describe? I understand it, but how would you describe?
All right, mathematically, what would it look like?
Yeah.
For any question like this, okay, the question is, when you jump and land on a mat, why do you flex or fluctuate your knees a little bit? Why do you bend? What is it doing? For any gymnast, what are you doing really? In words, not in physics words, but in general words, what are you doing when you land? You land like this, instead of just landing on flat legs like that. Yeah, it doesn't hurt as much, but what are you physically doing? You're what?
You're breaking the fall.
Breaking the fall is the term you use, good. Now I use more of a physics term. Absorbing the energy or shock. Either one's fine, good. It's like a shock absorber. Remember your car has shock absorbers I talk about that minimize the vibrations? What you're doing there is you're absorbing the shock. So, to answer Peter's question mathematically, here's what's happening. Look at this formula here. If I'm falling with a given velocity and I come to rest, I have a certain change in momentum. I can determine that change in momentum, but it doesn't matter. If I come to rest in 10 seconds, if I come to rest in 2 seconds, I still have the same change in momentum. Remember that momentum is my final momentum minus my initial momentum. If this is 0 because I'm coming to rest, whatever my initial momentum is what's going to go in this formula. So think about any of these problems where you're causing something to stop. When the final momentum is 0, you're just left with this. Bless you. Now, this quantity right here is fixed. It depends on your mass and your initial velocity. That's what it really depends on, right? The mass and the velocity. This is the velocity before impact. So if you were falling from a shelf like this, it's the velocity right before you hit the ground that you would use here for this one. But this is a fixed number. It's not changing at all. It does not matter. You're free fall. Now, what matters is if you bend your knees. When you bend your knees and you land, you're increasing the time of contact. So if I land and just land like this, that actually hurts my head. You can feel it. You land, and the time of contact is like maybe 0.1 seconds. But if you were to fall off something and land like this, your time of contact is like a full second that you absorb the shock. So think about this mathematically. Pick a number for PI. 7. Okay? If the time of contact is 0.1, right? If you stop instantaneously when you hit the ground, really quick, figure out what your force would be. Divide by 0.1. You can do it in your head if you want. 70, right? Your force would be 70. Now, what if instead of taking 0.1 seconds, you land and let your knees absorb the shock and it takes you 2 seconds? Okay, we do the same problem. The change in momentum is still 7 because you're still moving with an initial momentum of 7 and you're coming to rest. But now instead of taking 0.1 seconds, you take 2 full seconds to land. And you do this. What's the force now that you're going to feel? 3.5. Look at the difference in the forces felt. If you absorb the shock and take a longer amount of time, the force you feel is much less. That's why that example, if you remember the first example I gave you was the egg toss. You catch the egg like this, so you absorb the shock over a long time period. The force that the egg feels is much less than it would feel if you just catch it like this. It's the exact same answer as the gymnast question from your problem set. It's identical. Any question like this is absolutely identical. Anytime that something lands and you do like soft hands, or if it lands and there's springs in the bottom and the springs absorb the shock, you're increasing the time period of contact, so you're therefore decreasing the force felt. That's physically what's happening. You're increasing the time of contact and decreasing the force felt, and as a result, you get a lower force than you would have if you didn't have that shock absorber. The reason all goes back to the fact that your change in momentum is not going to be different. If you change momentum by 7 or 40 or whatever it is, that means it's going to be the same change in momentum, even if you take longer to absorb the shock. Okay, that does not change this value on this side. What are the questions about 6? That was 6-1, really. 6-1.
Wait, going back to like if you have to solve for the impulse, so like I don't get what you'd be given to solve.
All right, ready? Situational problem. Write it down. The mass of an object is 5 kilograms, and it travels with a velocity of 7 meters per second. 5 kilograms, and it travels with a velocity of 7 meters per second. After some sort of collision, the velocity is now negative 4 meters per second. Determine the impulse on that object. Not the time, not the force, but the actual impulse felt.
Wait, who is P2?
Again, the mass of an object is 5 kilograms. It starts with a velocity of 7 meters per second. After a collision, its velocity is now negative 4 meters per second. Determine the impulse felt by that object. The velocity before impact is 7 meters per second. After the collision, the velocity is negative 4 meters per second. And we know that our change in momentum is equal to impulse. This is impulse. So you're not asked to find force, you're not asked to find time, but you're asked to find the change in the object's momentum, really. So go ahead and figure out the change in the object's momentum. MVF minus MVI. Relax, ladies. So, this itself is the impulse. F times t, that quantity, is defined as impulse. So if a problem ever says, because this happened in your homework, I think, one of your homework examples, it said determine what the impulse is that the object feels. This is the impulse. It's not a force. It's not a time. It's something different. It's the product of those. Now, if I then followed up with part B, so that's part A. Find the impulse felt by the object. You got it. It's negative 55 kilogram meters per second. Then part B says, if the time of contact is 3 seconds, find the force felt. Well, then all you have to do is plug in a 3 for time and divide by 3 on both sides. So this could be a multi-step math problem at the end of your test. Okay? So divide by time, whatever the time is, and you'll figure out the force felt. Or the problem might say, find the time period that the contact should occur so that the force is not greater than 100. So just set the force equal to 100 and determine the time period. And that could be the amount of time that you need, at least that much time. If you have more time of contact, the force will be even less than 100. That's even better. So if I told you that the maximum force that I want to feel when I land is 25 newtons, I go like this. Now, if I feel force when I'm landing, it's going to be negative because it opposes my motion. So the maximum force I want to feel is 25 newtons. I then solve for t like this. That's the maximum force I would like to feel. No more than that. So I divide through, giving me positive 2.2. It would be a negative 25 for force because remember that when something stops you from moving, like in this problem, you're moving positively, then afterward, aren't you moving negatively? Look at your original problem. You started moving positive and then you were moving negative. So what has to happen for you to stop and move this way? A force needs to be pushing you this way. Therefore, it's a negative force. Okay? So this is the time period you need of contact, or more than that at least. Because if you have more time than this, remember from momentum impulse theory a minute ago with the gymnast landing, if you take more time than this, your force goes down even more. If you take even more time, it goes down even more. So you need at least this much time, at a minimum this much time.
So when you ask us to solve for the impulse momentum, you really solve for that time speed.
Yes. If a problem ever says find the impulse, you're really solving up here. You're solving right here. You're finding the product of F times t, which is really just the change in the object's momentum.
So do you have to think the amount of time it takes your negative 25 minutes to develop that force?
Sure, negative 25, not 2.5, but yes. 25, yeah.
Is it negative 25 or not?
Yeah.
Okay, that's what I was saying.
Okay. So that's the time you need, at least that much time. You could have more time than that. You have to understand why that is true. If it takes more time, right, if this number increases, this number will then decrease. These force and time are inversely related in this relationship here. If there's more time of contact, if I absorb the shock more, it's less force. So if I want this to be the most force I can feel, it means I can feel less force than this. So for this to go down, this could also go up a little bit. I could have more time of contact.
I know this was asked, but could you please explain again where the force came from? Where did you just put that in there?
I just put that in there.
Okay.
I picked a number, yeah. I said, if the max force you could feel is 25 newtons, find the time period.
Okay.
So that was like a part B follow-up from part A. All right, let's look at 6.2. 6.2 and 6.3 are really, similar sections. 6.2 is about conservation of momentum. Okay, conservation of momentum, which led us into 6.3, which dealt with inelastic and elastic collisions. So here's your formula. Okay? Now, anybody have the formula sheet loaded on their iPad? Can somebody just pull it up that's in the front row over here? Thanks, Julie. We got a cumulative formula sheet. It probably has a C in front. Yeah?
Dan Cooper.
She beat you. That's all right. Perfect. Okay, so I give you the formulas. All right. So you know what? I didn't realize that I did this. I was nice. So on your formula sheet, if you take a look, I'm going to maximize yours for a second. I give you these 4 formulas for this chapter.
Ooh.
So make sure you're familiar with them on your formula sheet. So I give you momentum formula, momentum impulse theory, elastic collisions, inelastic collisions.
That's
So that's already on the formula sheet.
That's all the
Okay, so feel free to just peruse that. But that's what this is, right? That's what this formula is. Given a scenario, you have to identify what's there and what's not there. So, let's say that, I don't know, 2 objects start together. So this is kind of backwards inelastic. It's backwards. They don't end up together, but they start together. Two objects start together and they are moving together. So imagine, here's an example, all right? Me and this coil of wire are walking together, we're moving together, and then I throw the wire backwards, okay? So we're moving together first, and then there's some sort of an explosion, which is the opposite of a collision, okay? There's an explosion that occurs, causing the wire to move backward. This is like the dump truck one, the pickup truck, with the steel beam in the back, and the beam slid out the back of it, causing the truck to speed up because it lost some mass. That's what happened with me there. I just dropped some weight. Okay, I sped up a little bit. So imagine a problem like that. How would you write the formula? Two objects start together, moving with some given velocity, then they somehow explode and separate into two separate entities. What would it look like?
It's that one formula we always use it backwards, right?
Yes, so tell me what it would look like.
M1 plus M2 VF.
Well, in this case, instead of VF,
VI, right?
because they're together before the explosion,
Sorry.
then,
V,
listen,
M1 V, yeah, is it?
well, V1F, let's specify that object's velocity, plus.
M2 V2F.
Good. Okay? So you need to be able to manipulate things. You need to be able to change the problem. So let's imagine now for a moment that I did the exact same thing. Okay? Ready? I'm moving with the coil of wire, but then as I'm moving, I drop it right there. So it's not moving after the collision. It just stops moving altogether. What that would do is, it would say, imagine this is me, and this is the wire. It would make this value go to 0. You follow what I'm saying? It went from moving to instantaneously just not moving. Maybe I was walking like this, right? And there was like a hook along the wall and I got caught on the hook and it just grabbed the hook and it stopped and I kept moving. It would be like I'm losing that mass along the way. So that would drop off. Or maybe I take as I'm moving this way, I throw the object, I'm in space, and I throw an object that way to propel me this way. If anybody's seen Gravity, that was one of the few things they did right in that movie. Okay, I mean they did a good amount of things right, I should say. But in one part, they talk about if you're stuck out in space, what you would do is you throw an object one way, what would happen?
That's a problem.
It would push you back this way. Because remember, momentum is conserved. So this would be the exact example right here. At first, you're together. Imagine you're drifting off into space. Okay? You're drifting off into space this way, but your spaceship is there. So together, you and say you have a oxygen tank in your back. You and the oxygen tank are moving with some velocity this way. You need to turn your body, throw the oxygen tank that way to propel you back this way. That would be the scenario, but without crossing off the wire. So every one of these scenarios is the exact same thing. That's what I keep trying to emphasize this. It's all about analyzing into the context of which formula you're going to use. But the ideas are always the same. There's some sort of either collision, where two objects hit and separate. Or there's a collision where they hit and stick, or they start together and then they separate. Those are really the three scenarios. This is the only one that's not on your formula sheet right here. It's not on your formula sheet because it's the same thing as the other one on your formula sheet, just backwards. Instead of VF, this is VI. Instead of these being VIs, these are VFs on the right-hand side. Okay, but it's the same one as that last formula on your formula sheet.
So was this
6-3, really. 6-2 and 6-3. Conservation of momentum. Now, what about the last piece with inelastic versus elastic? What's the major difference? Conceptually, not mathematically, conceptually. Jack, help us out.
With like elastic collision, you have two objects starting like not together and then end up not together.
And then, continue.
And then inelastic is like you can have two objects starting together and then separating after collision, or you can have two objects like not together and then after collision they bond together.
They bond together, good. Now what happens in the process of that bonding or that exploding with inelastic? Remember, inelastic, to start together and separate, something has to happen. To start separate and end up together, something has to happen. There has to be a what?
The energy is conserved in elastic movement.
Okay, so I asked about inelastic.
Oh, and it is not constant.
So what's happening conceptually? Don't just read the notes back to me. What's happening conceptually?
Got me.
There's some energy loss. Very good, John. So the idea is this. In your lab, you did this, the lab that was due today. You found out that delta KE every time. Okay, which is really like KE final minus KE initial. And you got a negative answer every time. If you put the positive value, because you said, oh, that's Q loss, that's fine. But let's say that your final kinetic energy for the problem is 20 joules. Well, beforehand, it's got to be something more than that, because you used energy to fuse together. So let's say before that it was 27 joules, therefore it used 7 joules of energy for that object to fuse to the other object. Okay, was the other example where a pellet gun is fired into a little clay cart. The pellet bullet embeds itself into it, causing the cart to move. Well, the question was how much energy was used, and that would be your solution there.
It's always negative, right?
Yeah, it's always going to be negative in these cases because you're losing energy in the system. Some people wrote their formula on theirs, and I looked and I saw some of your labs that were uploaded already. Some of you did this formula, which is okay. And solve for Q. In that case, you'd get a positive number because you're finding what Q is. All right, because you then, how would you solve for Q? Look at the top right. When you subtract KEF,
Yeah.
so it'd be KEI minus KEF. What is this? That's why this is a negative quantity here, whereas if you solve for Q, you'd get a positive answer. What matters is the value itself, the magnitude, and your conceptual understanding that that energy is going into the fusion or the separation of that object.
So like when you're doing inelastic problems, you're always going to have the KE.
You're going to have to find KEI and KEF and find the delta.
For elastic problems, we're trying to make sure that the KE values match up.
Yes, very good. And that's the second part to this. So, for elastic collisions, energy is conserved. Again, in real life, collisions are somewhere between elastic and inelastic. Okay, but for elastic collisions, energy is conserved. So you are trying to prove that you have the same amount of KE before as KE after. So again, you calculate them, but you should get a delta KE of 0 because there's no energy expended.
Yeah.
So if it's like 30 for KEI, it's 30 for KEF. And that is for elastic collisions. Okay?
What's the example of an elastic collision? Like a strictly elastic collision?
Elastic?
Strictly, yeah.
Would be like 2 pool balls or billiard balls getting together and colliding. Again, none of these are really elastic. You know that. That's what I'm
No,
saying.
that's what I'm saying. Is there anything that's completely elastic?
Sure, in outer space, if you had something where there was no air resistance, there was no frictional loss, and 2 objects that were solids that hit and did not deform, but realistically, everything is really between the 2. Okay? But I'll say on the test, assume that's an elastic. The reason you assume some things are elastic is because they're so close to elastic that it might as well be, and it simplifies matters for everybody. Julia?
And your kinetic friction is always going to be less than your initial.
Kinetic friction.
Kinetic
Kinetic final and kinetic initial.
Yeah.
Final will always be less than initial for inelastic collisions. For elastic, they're the same, right? I'm trying to think of what else conceptually. Because I feel like mathematically we've really pounded this one in, right?
Yeah.
And we've done so many problems with mathematically compared to like the conceptual stuff that it doesn't make much sense to do. I'm trying to think of examples. Oh, a good example that some of you struggled with. What's that?
Are you going to do like the... No.
Go ahead.
You know, for the short answer one, the one with why it would hurt less.
Yeah, that's a good conceptual example. Absolutely.
Yeah.
For mathematical, though, I'm saying the ones that were tough were where, remember there was like an unknown mass in the problem? You have to solve for m, made it a lot harder than solve for v. You had that in your lab in that 4th example. Okay, and in section 6.2 of your notes, we did an example where you're solving for an unknown mass. Or I could tell you, remember another example? The mass is given as m, and the other object's mass is triple that. So you use 3m. I don't know. I'm trying to think of other math examples that could be tougher. What questions do you have? Not going to be a long test. I can tell you that one for sure.
Really? It's not long.
Not in length. No, I mean, it was only 3 sections of the test. There's only so much multiple choice I can really ask you.
Like,
Okay.
are they going to be more written, like verb? I don't know.
I would estimate
Not so much on the math and multiple choice.
3 math,
And
probably
multiple choice.
3 long.
3 or 4. Choose 2 or choose 3 depending.
All multiple choice?
No, math, of math. Multiple choice, I'm going to guess, I'm going to do like 5 or 6. And short answer, probably like 3 or 4 of them maybe.
So what's it going to be out of the test?
I haven't finished it yet. I have the math ones written so far. So you can expect between 3 and 4 math, about 3 short answer, and between 4 and 5 multiple choice. Pretty much the same format as your conservation of energy setup was. Yeah. Short answer, usually conceptual. You should definitely be able to do problems that say the following. All right, ready? Let's do this one. Let's say doubles and its velocity triples. What is the change in the object's momentum? So again, an object's mass doubles and its velocity triples. What is the overall change in the object's momentum? What is the overall change? By what factor? Good. It's an increase by a factor of 6. Remember how to do this. I went over this with kinetic energy. If you see a change in a variable, replace that variable. So normally the formula looks like this, right? This is the normal formula. Well, I replaced M with double M. I replaced V with triple V. And I get 6MV. Well, how does this change from here to here? Well, there's a factor of 6. That's an increase of a factor. What about this one? The mass of an object triples and the velocity is cut in 4. Cut in 4. Find the net change in the object's momentum. Again, write it down. Or do the math right now at least. The mass triples and the velocity is cut in 4. Find the overall change in the momentum of the object. So normal momentum is here. The mass triples, so what do I write? The velocity is cut in 4. Alright? Does that make sense, what we're saying here? So what would you say then? This is where it gets difficult.
3/4, 0.75.
Yeah, you could say it's 3/4 of the original momentum. It is 3/4 of the original momentum, mv. Remember, this is the original momentum. It's right here, right? That's the original momentum still. So if you were writing a verbal statement for like a short answer for part 2s, you would say, the momentum of the object is now 3/4 of what it was initially. Okay? You can't say it's a factor of increase or decrease because that gets a little bit confusing because it's decreasing, but it's not decreasing by a factor of 3/4 actually. You can't really say that statement. It's not mathematically sound. Okay, so you would say it's 3/4 of what it started with. Trying to think of what else.
Office hours tomorrow?
Yeah, office hours tomorrow after school. Okay. Come on by tomorrow after school. What other questions do you have from your problem sets? What is stuff that's been confusing you?
They weren't that bad.
They shouldn't have been, right?
No, I feel like
All right.
all of them in class.
I mean, we did all those examples in class.
Yeah.
You did a worksheet. You did a lab with like 8 examples in the lab. So by now it should be almost like annoying, if anything, right? The problem set should have been like, haven't I done this enough already? Which is fine. I'd rather be that than like you not be prepared. If you're at the point where you're like, this is so easy, it's ridiculous, that's great. It's a good thing. What you should really study are the problems that are more complicated, like you're not given a mass and you have to find mass, or you're told that the mass of one object is 4 times the other object. So use m and 4f. You want to do one of those? All right, sure. So I'm going to set it up. We have 3 minutes. Listen, you want to hear this kind of example. So, object A. Object A. Why don't you just get up and walk around? Object A has a mass that is 4 times that of object B. Object A has a mass that is 4 times that of object B. So here's what I'm thinking already. Does that make sense, what I've written? The mass of object A is 4 times that of object B. Now, you are more than welcome to pick a number for mass. You could pick mass is 1 for object B, so the mass will be 4. Or make this 2 and 8, or 3 and 12. It doesn't matter right now. But if your goal of the problem is to find the mass, then you can't do that. Again, if the goal of the problem is to find a velocity, you could pick numbers for mass and just make them 4 times the other. But if the goal of this problem is to find the mass, you can't pick numbers. You have to solve for m. So let's say the following. These objects collide, and before the collision, object A has a velocity of 5 meters per second, and object B, before the collision, has a velocity of -3 meters per second.
Right. What's the velocity on the board?
Object A has a velocity of 5 meters per second before the collision, and object B has a velocity of -3 meters per second before the collision. If the velocity of object A after the collision is 4 meters per second, find the velocity of the other object after the collision. All right, so the objects hit, they separate. Your goal is to determine VBF. Well, B and A are the same thing as 1 and 2. Okay, B and A are the same as 1 and 2. So before the collision, I've got mass of object A times its initial velocity plus mass of object B times its initial velocity equals mass of object A times its final velocity plus mass of object B times its final velocity. B and A are the same as 1 and 2. I'm just mixing it up so you see that it makes no difference. Okay, it's the exact same formula that you have on your formula sheet right here. It's identical, except for A, put a 1 in, and for B, put a 2 in. Now, if our goal is to determine VBF, we know that the mass of object B is quadruple it. You could start by putting a 4m here, m here, m here, and a 4m here. And then you know the rest of the numbers. 5, -3, 4, and your unknown. So you can solve for this unknown over here. What you'll notice, there's a plus sign in here somewhere, sorry, is that m is in everything. So m can cancel out. That's why you could just pick a value for m. Make m 2 or 3 or 4. But if you were trying to find the mass, and I gave you VBF, you'd be searching for a little m in the problem. So don't automatically cancel it out. Depends on what you're trying to search for.
If you solve generically at first, you have to use the m's, right?
Yeah, but again, once you plug in the m's, like m and 4m, you'll see the m's drop off. Okay? But yeah, if you solve generically, leave it like that, and then plug in 4m and m for those locations.